This section we're talking about relating elements in our vector space to our bases using vectors in Rn. And so we've been talking about vector spaces this whole chapter, and bases are what we discussed in the last section. And so like it says here, bases are useful because you can use them to recreate any vector in the vector space. In other words, if we've got some basis, beta equals b1 through bn, so these are the basis elements. If that's a basis for vector space V, then every single vector in V can be written as a linear combination of those basis elements. That's what we saw in the last section, and so you should just maybe take another look at that section if that doesn't sound familiar. Notice here that we're doing we're doing linear combinations of the basis elements, and so another way to sort of express this is that x would be in the span of those basis elements. Right, so every single x in the vector space is in the span of b1 to bn, because they are equal to some linear combination of them. Now this section focuses on what we call the coordinates of x, or the beta coordinates, or something like that. And so that's what it says in this next definition here. So given some x in the vector space, some vector in the vector space V, and some basis beta, we call this set of scalars C1 through Cn. So the C1s that are the same thing in this definition are the same ones here. So the C1s that allow you to rebuild that vector using the basis elements is called the coordinates of x relative to the basis beta, or sometimes a little bit shorter way to say that is just the beta coordinates of x. And so you can see this is the notation right here, right? So this is like the specific element x is inside there, right? And so it's saying for a specific element in the vector space with respect to that specific basis, these are the constants that you would use to add up these basis elements, these ones here, the b's, sorry, to get x. And so one way to sort of think about this definition, it's how the vector x, and x is a specific vector, how the specific vector x is constructed using the basis beta. And there's a couple words for it. So coordinates of x relative to the basis beta, the beta coordinate, sometimes it's also called the coordinate mapping, because it tells us how the basis, the coordinates that will map the basis to the element. So just kind of be aware of those different phrasings. You might see it phrased differently in the book or the homework or things like that. You should just be aware of those things. And so notice that it's a vector of constants, right? So it's a vector in Rn, and this is a nice thing that we're going to be able to construct no matter what vector space we're in, even if we're in an abstract vector space. And so let's do an example in Rn, and then we'll do an example, if you look on the next page, we'll do an example of something in a more abstract vector space, P2 in that case. But let's start with the simple ones, sort of a simpler one here in Rn. So these are our basis elements. It turns out that these two vectors are a basis for Rn, R2 specifically, excuse me, we're in R2 here. And we're going to reconstruct this specific vector, which is 4, 0, using those basis elements. And then the constants that allow us to do that will be the answer here. That will be the coordinate vector for that specific x. And so the idea here is we want to find the linear combination of b1 and b2 that equals c, right? And so we want to find some c1 and c2 such that c1 times the first vector, 1, negative 2, plus c2 times the second vector, 5, negative 6, equals the vector we're trying to construct, x, 4, 0. Right? We want to find linear combinations of the basis elements that equal the vector we want, which is exactly the definition right here, right? We're trying to do x equals some linear combination of those things. x equals some linear combination of those things. And this turns into just, this is a linear system, a 2x2 linear system that we can solve in an augmented matrix. So we can take this linear system and solve in an augmented matrix. So let's do that. So, it just becomes a 2x3 when you put it in with the augmented matrix. And so let's see what that looks like. So that would be our basis elements. We want to find linear combinations of those things. And we want it to equal 4, 0, our given vector. And so we're kind of solving like a, c equals x here, right? Where the c is going to be our constant vectors. I guess it's not really c, it's going to be the coordinate vector. So it's really this x sub b. So it's like a x sub beta equals x. This is the system we're trying to solve here. And so the solution is going to be what we're looking for. And so that's a really easy linear system to solve, right? Just row reduce it. So I did RREF. And it turns into this. And so we get, we get a solution. We get a unique solution. And more specifically, the C1 and C2 in this equation right here above is C1 is -6 and C2 is 2. And so these are the coordinates that map our basis elements to the specific vector x. And it's a really easy thing to check. I'm just going to write down the check here because you can always just do a quick check and see if that actually makes sense. So -6 times the first one plus 2 times the second one should equal 4, 0 is what we said here. And so -6 times 1 minus 2 plus 2 times 5 -6. That's going to equal, let's see here, in the first one we'll get -6, 12. 2 times the second one is going to be 10, -12. And when we add these things up, we get 4, 0. And so check, it actually worked. And so our coordinate vector, the beta coordinates, the coordinate map, whatever you want to call it up here, is -6, 2. And so what we just found was the coordinate vector with respect to this specific basis is -6, 2. This is sort of the final answer here. And so you can see here, this is a way we can relate the specific basis elements, which in this case were these ones right here, to this specific vector using those specific constant weights. And bases are not unique. We've seen a couple bases for R2, for example. And so if you had a different basis, you'd have a different coordinate vector. That's why this sort of value down here is kind of important. It's saying with respect to this specific basis that we're using. Okay. There is sort of another way to think about solving this system, though. And we're actually going to see it a little bit later in this section. So I just want to mention the other way to think about solving this using the inverse. So let me just add a couple comments down here. Notice that the other way we could have solved for this thing, we set it up as a linear system, put it in an augmented matrix. That's a perfectly fine way to do it. Excuse me. Another thing we could have done, if we could write the system as a matrix equation, so we could have written it like this. So basis elements in a matrix. The C1, C2 we're looking to find. We want that to equal our given vector. Right, this is like, again, AC equals X. And so we could have done this because the other way we could have found C1 and C2 instead of doing the augmented matrix thing is we could have found the inverse of this matrix, multiplied on the left, and then solve the system that way, right? We talked about how we can do that from the inverse section. And so we know that this has an inverse because the determinant's not 0, right? So we know that, for example, if this is our matrix A, the determinant of A would be AD minus BC would be -6 plus 10, so that's going to be 4. And so since it doesn't equal 0, we know that the matrix A is invertible. And so we could find these C's by multiplying by the inverse. So we could find C1 and C2 by multiplying for 0 on the left by the inverse. And we're going to do this more on this later. We'll do this later in the section. But just be aware, like, there's other ways to solve linear systems that we've learned in the class. For example, multiplying on the left by the inverse. And that's something that could potentially apply in this particular situation. In other words, there's more than one way to solve a linear system, as we've seen. Okay. So this is an example of vectors in Rn, right? So we're in R2 here specifically. We're using basis for R2. We've got a vector in R2, and so this was everything in R2. Let's look at one that is an abstract vector space of the set of polynomials. And so here we are looking at that now. And this is a new basis. So this is a new B1, B2, B3. Right, there's 3 elements in there. And it turns out that these 3 elements, which are polynomials, is a standard basis for P2. Take a second and try to remind yourself what P2 is. It's polynomials of degree 2. So polynomials of at most degree 2. And so when we say this is a basis for polynomials of at most degree 2, it means that any degree 2 polynomial you can think of, for example, the one written right here, can be written as a linear combination of those 3 elements. Kind of surprising. We saw sort of the basic basis for P2 in the last section, and this is a non-basic basis. And so we want to find constants that we can multiply by each one of these things, add them together, and equal this vector here. And so let's write down the math system here. We want to be able to multiply C1 times the first element plus C2 times the second element plus C3 times the third element to equal our given vector. Right, that's sort of the math setup here. That's linear combinations of our basis elements equaling the vector we want to figure out. Now, what we can do is we can obviously distribute the C's through those parentheses, and then we can group like terms and see what we want the constant to be, the t constant to be, and the t squared constant to be. And so let's go ahead and multiply this out. I'm going to sort of skip some steps here, but you multiply this out, you sort of distribute the C's, and then you group like terms. So distribute the CI's, and then we will group like terms. So I'm going to get all the t squared things together, for example. So when I group all the t squareds together, it comes with minus C1 minus C2 plus C3 t squared. So when I multiply that out, those are the t squared coefficients. When I multiply it out, this is the t coefficients, C2 minus 2C3 t. And then the constants end up being C1 plus 2C3. And again, we want that to equal our given polynomial. And so this is a nice form because we can kind of see, like, this is the coefficient in front of the t squared. Well, we want the coefficient in front of the t squared to be negative 6. Right? This is the coefficient in front of t. We want the coefficient in front of t to be 1. This is the constant. We want the constant to be 3. And so we can set up a linear system using the thing we just found here. In other words, what we just found is we want this first thing, minus C1 minus C2 plus C3, to be the t squared coefficient, negative 6. We want the second one, C2 minus 2C3, to be the t coefficient, 1. And then we want the constant, C1 plus 2C3, to be the constant, which is 3. And so this is a system of 3 unknowns with 3 equations. We can stick that in a matrix and solve it pretty straightforward, right? So this turns into the the augmented matrix, I mean minus 1, minus 1, 1, 0, 1, minus 2, 1, 0, 2. And we want that to equal minus 6, 1, 3. Real easy to row reduce that and get our answers, right? You RREF, and you get this matrix. So the left-hand side turns into the identity matrix. That means we get an exact solution, a unique solution. And then these are our coefficients. And so when you plug, C1, well, let's write down the solution. So this is telling us, this solution here is telling us C1 is 7, C2 is -3, C3 is -2. And so when you plug those values, right, into our original expression here, we'll end up rebuilding the matrix we wanted to build. And so this is the coordinate vector for this specific vector, this specific polynomial with respect to this basis. And so the final answer, the way we write that is the polynomial we were trying to recreate with respect to that specific basis beta equals the solution we found, 7 minus 3 minus 2. It tells us how to recreate this p, the p we were given, using the basis we were given. Those are the coefficients you would use. And so, notice how, let me just maybe pause a second if you're writing. I guess maybe you can pause the video if you ever need to catch up writing. But the interesting thing about this is we're relating this abstract vector space, this P2 vector space that is polynomials, but we're connecting it to the basis using a vector in Rn. And so keep that in mind, right? The things over on the left-hand side of this are in abstract vector spaces, this polynomial space. But the thing on the right is always going to be an Rn vector in Rn. So more on that in just a second here. Before we look at that in a little more detail in the next couple pages, let's look at another abstract example where we're given, we have the same set of elements, right, the same set of polynomials we just saw on the top there. And this set of polynomials is not a basis anymore. Let's consider the standard basis for these polynomials. And so this is no longer a basis. We're considering this to be the basis. And let's use this basis to find the coordinate vectors for these polynomials, right? And so this is like a v1, a v2, a v3. These are 3 vectors in our vector space. And this is our new basis. And this is what we call the standard basis for P2, which we saw in the last section. And so these would be our B1, B2, B3, our basis elements, right? And so what we're trying to do here is find the beta coordinates of each one of these vectors, which is pretty easy, right? Like if this is the only constant, the 1 is the only constant, well, that's what you're going to use to recreate the constants, right? You're going to use the t to recreate the t terms, and then the t squared is going to be used to recreate the t squared terms. And so we're going to find the beta coordinates and then show how you can use the beta coordinates to test for linear independence. And so let's first find the beta coordinates. Right, so we're going to use the beta coordinates to test for linear independence. So first find the beta coordinates for each v sub I in that set. And so it's pretty easy using the standard basis. Like you don't have to do this linear system like we did in the previous example up here. It's very easy to see that in our first element v1, which is 1 minus t squared, well, if you want to get a 1, you just do 1 times that element, right? When you want to get no t's, because there's no t's in that, you do 0 times the second one. And when you want to get a t squared, you do minus 1 times the third one, right? So that first element, 1 minus t squared, v1, is 1 times b1, which is 1, plus 0 times b2, because there's no t's, minus 1 times b3, because there's a negative t squared. Right? And so, in other words, the coordinate vector for v1 with respect to this element, this basis beta, is 1, 0, minus 1. So it's literally just like the coefficients that you need to use for those things, right? And so similarly, we can kind of easily write down the other beta vectors, right? So the beta vector for the second one is going to be 0, 1, negative 1. And so the beta vector for the second one is 0, 1, negative 1, using that same thought process. And the third one, just doing the coefficients, is 2, minus 2, 1. And so these beta coordinates relate these standard basis elements to each one of those elements in that set. And so then we can use those to test for linear independence, because if these vectors are linearly independent, it means that those basis elements are also linearly independent. And so we know how to test for linear independence using vectors in Rn. Right? So test for linear. So first find the beta coordinates. Second, let's test for linear independence of the BIs. And so we're going to take their beta coordinates, put them in a vector, or in a matrix, excuse me. And we're going to see whether or not there's a free variable, because we know that when we have no free variables, that means that the vectors are linearly independent, right? Because we get the trivial solution to the homogeneous equation. So let's reduce that matrix, and we see it turns into the identity matrix. And so, let's relate this back to the inverse matrix theorem, right? We know lots of things just by looking at this. There's a pivot in every row, for example. That's something we see there. We see that if we wanted to solve the homogeneous equation, has only the trivial solution. Based on both those things, we see that, and since the fact that the matrix reduced to the identity matrix, we can see that A is invertible. Based on all these things, we know that the determinant is not 0, etc. Right? So we know lots of things when we see that a row reduces to the identity matrix there. And based on all those things, the IMT tells us the vectors are linearly independent. So by the inverse matrix theorem, the vectors are linearly independent. And so the cool thing is, what we just did is, we've got these vectors in this abstract space, but we were able to show that they're linearly independent by looking at their coordinate vectors in Rn. So you can kind of like take these abstract vectors, relate them to Rn in some way, and then use our tools from Rn to talk about linear independence. And so I just want to make that quick note about like what the heck we just did at the bottom here. So the point we just did, the point of this thing we just looked at was that the coordinate vector, vi sub beta, provides a way to test for linear independence of vectors in abstract spaces, abstract vector spaces. That's sort of the takeaway from this, is this gives us a way to relate vectors in abstract spaces to Rn. Okay, we're now going to connect this idea to matrices and linear transformations, and think about that just a little bit. You know, the last couple of pages were just like giving you the idea of what these coordinate vectors are, and then doing a couple examples of in Rn, and then also in these abstract spaces. And now let's relate it to matrices and linear transformations here. So that's what's on the next page, is the matrix representation is the first thing. Okay, let's read this definition. So matrix representations. Let's say X is an element in the vector space V, and let's say the vector space V has the basis B1 through Bn. So we're still thinking about the basis as being labeled with a beta, and it still consists of a bunch of B elements. Then we know that that vector can be written as a linear combination of the basis elements. That's something we've seen before. Now, what we'd like to introduce here is if we put all of these basis elements in a matrix together, that has a name, and that's called the change of coordinates matrix. And so let's label it P sub beta, and that's going to be, again, you're taking the basis elements and just putting them as columns in a matrix. And we call this the change of coordinates matrix. Okay, so that's a change of coordinate matrix, right? And we notice that X is a linear combination of these columns. And so that really means X can be written as like this matrix multiplied times these constants Ci, which is really going to be this matrix times the coordinate vector, right? And so let's see if you follow this then. So then this expression, so this X equals C1 B1 plus C2 B2 Cn Bn. So this reconstruction of X can be written as a matrix multiplication. So it can be written as this vector B1 through Bn multiplied by a column of C's. Right, you've got a 1 by n by 1, so that's going to create a 1 by 1, which is going to be this value right there. And so we see that this vector on the left is the vector we labeled P sub b, our change of coordinates matrix. And we know that this column of C's from the last couple of pages is our coordinate mapping vector, right? And so this column of C's is really just this. And so we could rewrite this one as that, right? And so really every X can be written as a matrix multiplication, which really looks like P sub beta, times that coordinate mapping. And this is a matrix times a vector, right? i.e., the X we were originally looking at equals this. This is the whole point of what we're trying to say here. And the idea here, right, this is a matrix, P sub b is a matrix, and we know that P sub b is going to be invertible because the columns are linearly independent because they're basis elements. So let's write that down. So since the basis elements are linearly independent by definition, right, in order to have a basis, you need to have linearly independent elements. That means that PB has an inverse, assuming if it's square. and assuming we're in Rn and we have a square matrix here. And so that means that we could multiply both sides of this equation by PB inverse because we're sure PB inverse exists. And so notice what happens when we do that. So I'm going to rewrite this expression. I'm going to leave a little space to multiply by the inverse. Except I didn't leave enough space to multiply by the inverse. Sorry, I wasn't thinking there. So I'm just rewriting this expression, this equation right here, except now I'm going to multiply on the left by P beta inverse. And again, we know it exists because the columns are linearly independent. And then we know that these two things multiply together to give us the identity matrix. And so what we really have, and so they really just cancel out, is that our coordinate vector that we were trying to find on the last page just equals the inverse of the P sub beta matrix times the vector we're looking to find the coordinate vector for. Right? So in other words, what we just found from this is that if we do PB inverse x, we get the coordinate vector for x. And so this is another way to find the coordinate vector. So we can use this idea, can be used to find the beta coordinates of x. So we're seeing we're relating it to matrices because the the basis elements can really just be put in a matrix, and then it turns out that's always going to have an inverse, and then when it has an inverse, you can just multiply the inverse of this, which is this, right, by the matrix or the vector you're trying to find the coordinates for, and then you'll find the beta coordinates. So instead of like solving a linear system, you'd instead be doing an inverse and then multiplying a matrix. So just like, completely different approach. You're doing completely different operations when you're doing that, but you can still get to the same exact answer. And so we're going to do an example of doing that right down at the bottom here. So using these basis elements, we are going to find the coordinate vector, the change of coordinates. First of all, we're going to find the change of coordinates matrix, and then we're going to try and find the coordinate mapping for that specific vector. And so let me just sort of summarize the relationship that we just found up here. We found that this relationship, x equaling p sub beta x sub beta, implies that this relationship happens, right? So I'm just going to start by writing that right at the top here. So if this is true, then this must be true. This is what we just found right above. We came to this relationship by multiplying on the left by the inverse. And so what we're going to do is let's find the change of coordinates matrix, and then we'll look at the inverse to find the actual coordinate mapping. And so I'm going to slide my paper up so you can see all this. And so let's start by writing down PB. So P sub beta, which we call the change of coordinates matrix. And it's what you get when you just put all the elements of the basis together. I'm going to split this page in half here. So we can do half of it right here and half of it right here. So we just take the basis elements, 2 minus 9, and 1, 8, and we stick them in a matrix together. That's that. And then we want to find the inverse of that so that we can multiply it on the left by x. Multiply x on the left by it, excuse me. And so this is a 2 by 2, and so it's really easy to find the inverse of that, right? We have a very easy formula for inverses of 2 by 2s. So double check the inverse section if you need to see this, but what you do is you do 1 over the determinant, so it'll be 1 over 16 minus 9, and then you switch the order of the 8 and the 2, so it becomes 8, 2, and then you switch the signs of the 1 and the negative 9, so it becomes minus 1 plus 9. And then, so this is then going to end up being 25 when you add those things, right? And so you end up dividing each of these things by 25. So it becomes 8 over 25, 9 over 25, minus 1 over 25, 2 over 25. So that's the inverse. That's the inverse of the coordinate mapping. So we did the first part of the problem. We found the change of coordinates matrix, and then we also found the inverse of that matrix. And now we want to do this part here, right? We want to find, we're being asked to find the coordinate mapping, and that's this thing, right? That's the coordinate mapping for x. And so all we need to do to find this is multiply x on the left by the inverse. Right? So we're going to take this x, multiply it on the left by the inverse, and then we'll find the coordinate mapping. So we do 8 over 25 minus 1 over 25, 9 over, oh, that should be 25. I don't know why I wrote 29 there. Let's see that. 9 over 25, 2 over 25, and we're going to multiply it on the left by x. And so this is my coordinate mapping, multiplying it, the inverse of the coordinate, the change of coordinates matrix. We're multiplying it by x, and that's going to give us what we want, which is the coordinate mapping. And when you do this multiplication and you add it up, you'll end up getting minus 3, 1. So this becomes minus 3, 1 equals x. And so this is the coordinate mapping for that specific x. And we achieved it via matrix multiplication by an inverse instead of solving a system like we had done on the last page. So, just sort of playing around with all the tools we have and thinking about how we can think about these things a little bit differently and approach the same question sort of in different ways. The last thing I'd like to just do is, sort of think about this in a linear transformation kind of sense, using a linear transformation kind of picture here. So let's take a look at this last page at this image here. So let's read what it says first. So the coordinate mapping. When we choose some basis, beta, for a vector space, what we do is we introduce a coordinate system for that vector space. In other words, the basis tells us a way we can represent every vector in the vector space, even if the vector space is not Rn. But even if it's not Rn, we still end up connecting the vector space to Rn. And so I've been sort of saying this entire time, but here's a picture, and we're going to sort of get into it in more detail. And so first of all, let's look at this picture. The x here is obviously in the vector space V, right? Looking at the picture. And so x is in this vector space V, and that vector space V is going to be associated with the coordinates for x via the basis elements in beta, right? So x is in V, and it's associated with the coordinate vectors using the basis elements. This should be basis and basis beta. That's what we've been looking at this entire time. And so the cool kind of thing is what's being shown here, right? This is obviously the vector space. V is the vector space that we're talking about. And then this is obviously Rn. And this is the coordinate mapping, right? So the coordinate mapping is sort of telling you how you can relate things in the vector space to the vector, some vector in Rn, right? So it's mapping V, the vector space, onto Rn. And the cool thing is this vector space over here may or may not be Rn. So over here, maybe this is Rn, in which case you're relating things in Rn to Rn. Maybe it's a different n, so maybe it's Rm, right? So maybe it's a different dimension that you're relating to the vector space. Maybe it's it's Pn. So maybe it's a polynomial space over here, or maybe it's even, there's lots of vector spaces. Maybe it's like matrices. This would be m sub n by n means matrices that are squared. And so it doesn't matter what vector space we're sort of talking about, whether it's abstract or whether it's Rn. The coordinate vector always gives us a way, so over here is always Rn. And so it gives us a way to take either of an abstract vector spaces and map them to Rn in some way, which lets us use all the tools we know about using in Rn, like row reduction and inverses and all these things that we've been working on. And that leads to this theorem, this culminating theorem here, which is if we have a basis, b1 through bn, and that's a basis for the vector space, then the coordinate mapping that takes vectors to that mapping is a one-to-one linear transformation from V onto Rn. So there's two things here, right? So it's saying that the coordinate mapping is a linear transformation, so two things. So that's sort of one thing. Not only is it a linear transformation, but it's a one-to-one linear transformation and an onto linear transformation, right? And so that is each specific vector has a unique coordinate mapping because that vector is associated with the coordinate mapping via the thing we saw on the last page, the inverse of the coordinate, what do they call that? The change of coordinates matrix. And we know that obviously it's invertible because it exists, which means it must be one-to-one. And since P inverse is obviously invertible, it must be a one-to-one by the IMT. So again, just trying to relate this back to linear transformations a little bit, a few things we've seen in recent sections, and also linear transformations. I'm going to stop here. Thank you for your attention.